Now come to the second biomolecule structures, the nucleic acid. The nucleic acid is quite complicated, so we have to study the structure of the nucleic acid from the very smallest part of the molecule of the nucleic acid first. So nucleic acid composed of basically the nucleobases, or it can be called as nitrogenous bases, or the base molecule with nitrogen atom included in the structure. And then from nucleobases, they can then condense with something else, constructing a bigger version of molecule, which is called nucleosides. And from the nucleosides, it attached or condensed with another kind of molecule. And at the end, you have nucleotides. And these nucleotides polymerized, and at the end you have nucleic acid as the product. So first of all, we have to understand the structure of the nucleobases, and then trying to understand the property of the nucleobase over here, so we can understand the properties of the whole nucleic acid at the end. So these five structures over here are nucleobases. Nucleobases can be categorized in two types of them. First of all, adenine and guanine. If you look at the structure, you have kind of two rings that fuse together. Okay, so the structure is very similar to this one. This is a kind of aromatic thing. Right? The aromatic molecule over here is called purine. The name of the molecule is purine. So both adenine and guanine can be called as purine derivatives. Okay? And for three kind of structure over here, uracil, thymine, and cytosine, is quite similar to another kind of aromatic molecule over here. So the structure is very similar to the benzene ring, but instead of carbon atom, we substitute two carbon atoms in the ring with N, okay, in position 1 and 3. So this is called pyrimidine. So three of nucleobases over here are pyrimidine derivatives. Okay, so we have two kinds of structure. Okay. The bottom half is the aromatic ring, and the top half is the fuse of two aromatic rings together. Okay. Because of the aromaticity, the things here are all flat in two dimensions, and every nitrogen atom, every oxygen atom over here performed sp2 hybridization in order to construct pi conjugator system for the stability of the things. Let us show you one of the example. Maybe the cytosine here. The cytosine, as you can see, they composed of aromatic ring over here, NH, and then NH2 up here. Okay. NH2 over here is not a base, it's neutral. It is a neutral compound actually, because even though we have electron pair over here, but this electron pair is not like simple amino group in your amine, because in the amine you have things like this, NH2, and this electron pair can act as a base, right? So this is because the amine normally nitrogen atom adopted sp3 hybrid. So electron pair on the nitrogen atom is sit in sp3 orbitals. So if you have H plus or any kind of acid, the positive charge and negative charge or electrons can react, right? So you coordinate electron to the H plus, and you have the salt, ammonium ion as a salt, as a product. But now for this one, NH2, instead of being sp3 like this NH2 will use sp2 instead. So if your NH2 using sp2, So everything is in 120 degree, right? And this electron pair is sit in the p orbitals. So why this shall happen? If you look at the structure in perspective view, I have 6-membered ring over here. This is the aromatic ring here, and I shall put nitrogen here and here, and the double bond oxygen is over here. So as you can see, N here and N here, you have p orbitals, right? Both carbon atom over here constructing double bond, you have pi bond over here, p orbital over there. And for CO, you also have like p orbitals. So all of these are in the same plane. P orbital connect together, right? So if p orbital connects together, we call this as the conjugated system, pi conjugated system, to be clear, because this is the conjugation of so many pi bonds that attached with each other. So we call this as pi conjugated system, conjugated system. Or we can call it as pi conjugation as well. Now, so if you look at this nitrogen here on the right, electron pair of the nitrogen is pointing 120 degree. So it's pointing outward to this kind of direction. But for NH here, again, this NH instead of sp3, like other amine, this NH can perform sp2. Because if this NH is sp2, adopting sp2, so this NH pointing 120 degree, you have electron pair in the sp2 over here. This let your pi conjugated system longer. An electron can resonance all along the pi conjugated system. So if electron can move along, that means the distribution of negative charge or of the electron is better than stay at any static orbit, right? But this can resonance. So if your electron moves, that means the negative charge is move, right? So if negative charge is move, that means the electron density is reduced by the moving of electron. So if electron density is reduced, then the charge density is reduced because electron is negative charge. So if the charge density reduced, that means the electronic potential energy is reduced. So the energy level of the molecule, of the whole molecule, is reduced. So that means your molecule is stable. Okay, so NH2 here, NH here is sp2. And again, you have NH2 over there. Where is it? It is here, NH2. So if your NH2 adopt sp2 hybrid, you can see that the electron pair of the NH2 is now in p orbitals, and make this kind of things conjugate with the whole system in the ring. So that means electron can resonance along the whole structure. So let me draw some resonance structure of this. Let's say if I move electron pair over here, making double bond over here. So the double bond here can move along, and electron pair, double bond here can move up to oxygen atom. As you can see, everything can move. So one of the resonance structure of this molecule or cytosine can be drawn like this. So the atom stay the same place, right? But now you constructing double bond and make your nitrogen positively charged. And then double bond is moving from here down there, and then pi bond cleaved from CO to oxygen, and your oxygen contain negative charge. As you can see, electron is moved, right? Even though this structure contains positive and negative charge, but it's quite okay because negative charge is on a very high En value atom, but the positive charge is on nitrogen atom which is low EN comparing with oxygen atom. So that means oxygen can withdraw electron from the system, from your nitrogen atom, and make your nitrogen atoms turn to be positive charge. So that's normal. That's normal. That's simple. And the molecule is more stable because electron is moving. If after it moving down, it can move wing upward, turn back to this structure as well. Or you can also draw the structure from the resonance stabilization of this nitrogen atom as well, like this. You move electron pair down here, this up and this up. So another possible resonance structure is like this. So you return electron pair back to the upper amino acid, the amino group, sorry, and then the oxygen atom still contain negative charge. The nitrogen down here is positively charged, right? So as you can see, this is another possible resonance structure, and you can return it back to this conformation by moving this electron down, making a double bond, pi bond, and then move it up here, move it down here, and then double bond, go back to the nitrogen atom, constructing the electron pair. So as you can see, to make this nitrogen be like this, trigonoplanar, right? So this nitrogen have to be sp2, right? Constructing this pi bond. So this is the proof. And again, this nitrogen atom in this conformation, sorry, not conformation, resonance structure, the nitrogen over here contains double bond and two single bond. So adopting what trigonoplanar and sp2 hybridization of nitrogen atom is required. So this is why every atoms over here have to be sp2 to let the electrons can move along in the pi conjugator system. Okay, so this is how cytosine, every atom over here is sp2. So again, for atom molecules over here is exactly the same. Nitrogen atom, oxygen atoms, everywhere, every place is over here is sp2. Okay. So what importance about this? So with sp2, you're constructing 120 degree, right? And yeah, as you know, we have kind of positively charged hydrogen atom because this one is connected with very high EN number, high EN value nitrogen atom, and you have electron pair, right, which is pointing to 120 degree over here from this picture as well. And the oxygen atom over here, you have electron pair pointing 120 degree by sp2 hybridization. So the direction of electron pair and the hydrogen atom, which is positive charge, that is available to making hydrogen bonding, right? So you have kind of exact direction, exact angle to perform hydrogen bonding between molecules. So this can constructing the network of hydrogen bonding in nucleic acid, as you may remember about the helix structure of DNA. So all that kind of things belong to this what hydrogen bonding, and this hydrogen bonding direction is caused by hybridization of this kind of molecules. Okay, now we know about the nucleobase already. So from nucleobase over here, we're going to condense our nucleobases with something else and make it bigger to be nucleoside. Now we're going to look at the structure of the nucleoside. Okay, now come to the nucleoside. Nucleoside is a kind of molecule condensed from between nucleobases and a kind of monosaccharide. The monosaccharide that I'm talking about is the ribose sugar. Okay. Ribose sugar is the second compartment of this nucleic acid. Open chain structure of ribose sugar is like this, with OH pointing to the right. So this is D-ribose. So from this structure, as you can see, we have aldehyde group on top, and the whole system we have 5 carbon atoms. So this is aldopentose sugar. So this aldopentose sugar can again undergo cyclization, and at the end we have this kind of structure. This is 5-membered ring structure of ribose, but okay, ribose sugar still can condense in and forming 6-membered ring as well. But ribose sugar in nature, the most stable form is the 5-membered ring like this, the pentagon over here. So after you have ribose sugar, as you can see, now instead of aldehyde group, you have only OH group in the molecules, right? We have 1, 2, 3, 4 OH groups. So this is a kind of tetraol, we can say that, or a tetrahydroxy compound. So as you can see from the previous topic, carbohydrate. No? First of all, you can find the glycosidic carbon, which is here. As you can see from the structure, this carbon contains 2 oxygen atoms attached to itself, right? And this carbon connects with C. 1C, right? That means you have another atom, hydrogen, pointing downward over here. This is aldose sugar. Now from ribose sugar, it can then condense with the nucleobases. So for nucleobase, it can be purine or pyrimidine derivatives, and all these, right? We have NH like this. I labeled the hydrogen atom with the blue color. So I shall use the same color code actually. From your nucleobase, N, and maybe 1 ring or 2 ring, whatever, the blue hydrogen from that picture can condense, right? And after that, you cleave water molecules out of your system. Right? So at the end, you have kind of this one, OH, OH, and a glycosidic linkage condensed between ribose sugar and your nitrogenous base. You have this kind of structure. Okay? So we have like 5 nucleobases. All these nucleobases can condense with ribose sugar, and then at the end you have the nucleoside. This is called nucleoside. Okay, nucleoside. So there are 5 possible nucleosides basically, right? But the name of the nucleoside is changed from this name of nucleobases to something else. So from the nucleobase, now you have nucleoside. Okay, so the nucleobase adenine, guanine. Both of these are the purine derivatives. No? So adenine changed the name from adenine to adenosine when it becomes nucleoside. This is called adenosine. And from guanine, it is changed to be guanosine. Okay. So this is the purine base. For pyrimidine base, you have a uracil, you have thymine, and also the cytosine. The way we call the name is changed, is different from the purine system. For your pyrimidine, uracil will be uridine. Thymine to be thymidine. And cytosine to be cytidine. Okay. You end with dine for pyrimidine structure, and you end with nosine for the purine structure. So that's all about the name. But yeah, the structure is quite simple. You just condense your ribose sugar with all these bases, constructing the glycosidic bond over here. So glycoside is the, nucleoside is the glycoside of nucleobase, and the ribose sugar, just that. Okay, so actually the nucleosides are glycosides. So the question is whether 5 of the glycosides formed by these nucleobases can undergo oxidation by Benedict test or not. Tick tock, tick tock. So if you can still remember the theory of monosaccharide and everything, you know that this one undergoes equilibrium between open chain structure and the cyclic structure. But after you make glycosidic linkage over here, you lack of OH. Right? If you have the OH, after hydrogen is deprotonated by hydrogen bonding, you can return back to the double bond, C double bond O, right? And you cleave this out and return it to the open chain structure. But now you don't have that OH. You have nitrogen instead. So you cannot cleave the CN bond very easy. So that means this structure cannot open out to be aldehyde back again. So if you have no aldehyde group, you cannot undergo oxidation by Benedict test. So this is reducing sugar, but this is non-reducing sugar. Actually, it's non-reducing glycoside or sugar derivatives. Okay, no? So this is the nucleoside. Now come to the last section, nucleotide. Okay. From nucleoside over here, even though you use you used up one OH group in the structure, but still you have 3 OH groups remaining here. So all 3 OH groups can perform chemical reactions as simple alcohol, like reacts with sodium metal, or condense with carboxylic acid, forming ester bond, thing like that. Okay, but anyway, you have 3 of them, right? The most reactive OH position is on your left hand over here, because the OH over here is just point outward from the molecules, but this 2 OH group is sit inside the ring. That means it's quite steric, right? So if you have other molecules going to diffuse inside and reacts with the OH. So this one is quite steric, right? It's hindered by the ring structure. But this OH is point out of the structure. So it's easier to be reacted with other molecules. So one of the molecules that we know is your OH can undergo condensation with carboxylic acid, right? And then the product from that kind of condensation is ester. Now, it's somehow very similar to that kind of esterification. But now the esterification that we need to make the nucleotide is not just condensation between alcohol and carboxylic acid. Now, instead of carboxylic acid, we are using phosphoric acid. So this is the phosphoric acid. So this phosphoric acid reacts or condenses with the alcohol. So it's quite similar to the condensation between alcohol and carboxylic acid. So I shall draw condensation between alcohol and carboxylic acid for you first. This is the alcohol, right? Oh, sorry. This is carboxylic acid, sorry. Again, okay, this is carboxylic acid. And this is the alcohol. So after condensation, you just get rid of water. Right? And this oxygen condenses with the carbonyl group. So at the end, you have C double bond O, O and R prime. So this is the ester bond formed by this kind of condensation process. Now, instead of using carboxylic acid, we are now using phosphoric acid instead. So what is the structure of phosphoric acid? So you substitute carbon atom with phosphorus in the middle, but your phosphorus still contains 3 of OH group over here. So this is phosphoric acid. So it's exactly the same as carboxylic acid condensation, right? But now you change the whole thing on the left-hand part to be phosphorus. Right? So this, instead of carbon, you have phosphorus, and after condensation, you still have two OH group remaining here in the structure. So this is the ester from phosphoric acid and the alcohol. So if you can still remember the way you call the name of ester of carboxylic acid and alcohol, like if you condense acetic acid and ethanol, you call this one as ethyl acetate. Right? Acetate is the ester of acetic acid. Now this is the ester of phosphoric acid. So ester of acetic you call acetate. Ester of carboxylic you call carboxylate. Now ester of phosphoric acid, you call this ester as the phosphate ester. Okay? So here you come back to the process. We have OH over here. The enzyme actually do the job, right? Because there are three possible OH to be condensed, but the enzyme choosing this OH to be condensed with the phosphoric acid. So I will draw the structure of the remaining part like this. Okay. You have the glycosidic with nitrogenous base. Now the oxygen over here going to condense with the phosphoric acid. So it's then attack onto the phosphorus. Right? So the phosphorus lost one of the OH. Condensed with the hydrogen from alcohol, leaving behind the water molecule. So this is the phosphate ester bond. So I labeled the pink color over here is the phosphate ester bonding. And the result from this condensation, you call this as nucleotide. So nucleotide, you have the center core of the phosphoric of the ribose sugar, right? And on the right-hand side of the ribose, you have glycosidic bond linked between your ribose sugar and the nitrogenous base. On the left hand OH, you condensed it by esterification with the phosphoric acid, and at the end you have phosphate ester group here. Okay, so this is the nucleotide. To name your nucleotide is very straightforward, because the nucleotide over here, you have one phosphate group attached on top of this instead of actually, you can attach more of the phosphoric acid to other OH group remaining here down here, right? But the enzyme do the job selectively, puts the phosphate ester here on the last carbon, last oxygen over here. So we call this nucleotide as monophosphate nucleotide. Okay, for example, starting from adenine nucleobase, after it condensed with the ribose sugar forming glycoside, we call that glycoside as adenosine. Now from glycoside adenosine, you're making one phosphate ester bonding, so we call adenosine monophosphate for the product. So similarly, from guanine, you have guanosine and then guanosine monophosphate, uracil to be uridine and uridine monophosphate, thymine to thymidine and thymidine monophosphate, and at the last one, cytosine to cytidine and cytidine monophosphate, which is very simple. So from this, you can also reduce the name. So here, from nucleoside, I change it to be nucleotide. So it will be adenosine monophosphate. So adenosine monophosphate is then abbreviated as adenosine monophosphate, AMP. So guanine will be guanidine monophosphate, uridine monophosphate, thymidine monophosphate, and then cytosine monophosphate. So these are the nucleotides, okay, formed by so many reactions actually. The glycoside formation on the right hand side, and then esterification with phosphoric acid on the left hand side. So at the end you have this nucleotide. So after you have nucleotide, the nucleotide over here can then undergoes polymerization, and as a result you have the nucleic acid at the very end. Now I shall show you the structure of the nucleic acid or polynucleotide. Hatta. Now after we have the nucleotide, which is, as you can see from the structure here. The core structure in the middle is the ribose sugar, and as I say, on the right hand we condense it with nucleobase over here, right, using the blue hydrogen. Okay, so after condensation with the nucleobases, you have the glycoside, right? By glycoside formation, you connect nucleobase with the ribose sugar, and on the left hand, the OH of the last carbon can then condense by esterification with the phosphoric acid, making this green color phosphate ester bond. Now, as I show you here, we have 3 of the nucleotide. So with the nucleotide structure, as you can see, you still have 2 OH group left in the ribose sugar moiety, and on the phosphoric acid, you still have 2 of the OH group. As you know, that the phosphoric acid OH can condense with the alcohol parts, right? So here, you have 2 chances. You have so many chances actually. You have 2 OH group over here, which is actually identical. This OH and this OH are exactly the same, right? Because the molecule is like tetrahedron, no? So this OH, this 2 OH is the same actually, but this 2 OH is not. But by the enzyme system, by the Biomolecules system, they catalyze the condensation using left-hand OH over here. So, as you can see from this thing, all of the ribose again condense with phosphorus, okay, and get rid of the water molecule out by condensed OH of the phosphoric acid here and the H from the ribose sugar. So you cleave out the water from the system. So after that, this blue oxygen condensed with the pink phosphorus. So what I can say, or what I can draw, is this one. So that means the phosphoric acid, instead of 3 OH group, you condense 2 of the OH from the phosphoric acid with hydroxy group of the ribose sugar. So this structure is called phosphodiester bond, right? Because your phosphoric acid connect with 2 alcohol, making 2 of the ester bond. So we call this as phosphodiester. Okay, so this is phosphodiester, connect alcohol down here and alcohol up here together. Okay, so at the very end, you're constructing the long chain of the polymer. Okay, so here, if I want to just draw it again, what I can say is that the blue oxygen up here of the ribose sugar can then condense with the phosphorus down here. And again, this molecule, the phosphorus condense with the next ribose on top. Then your ribose sugar down here can again condense with the phosphoric acid from the bottom unit, right? And again, on the very top over here, your OH of the ribose connecting with phosphoric acid from the second molecule. That means the phosphoric acid on the very top over here can then be condensed with the OH of the ribose sugar on the next level. So what we can see is at the very end, you have the polymeric structure of this kind of polymer. So the monomer or the building block of this thing is called nucleotide. So this one can be called as the polynucleotide. Okay, so I would call this one as the polynucleotide. Okay, so polynucleotide can be named as nucleic acid. Why? Because if you look at the structure, you still have the phosphoric acid OH, which can be dissociated, right? So we call this as nucleic acid because it's performed as simple acid because of the OH over here can be dissociated, right, by hydrogen bonding and everything. So after dissociation, you may draw it like O minus and H plus. Right. So in your biology courses in your high school, they always draw the polynucleotide in the form of O minus, O minus, and O minus. But actually, in the cells or in the nucleus, everything is buffered by the buffer solution in biological system, no? So we use like carbonate and phosphate and everything in the system. So that means the polynucleotide over here, or nucleic acid over here, is partially deprotonated. So some of the unit was deprotonated, some of the unit is in the form of OH, but some of the unit in the form of O minus. It depends on the pH. So normally the pH in the cells is about 7 point something, you know. So it's partially dissociated and controlled by the buffer system in the cells. Okay. So this is polynucleotide. The polynucleotide, as you may know, that we have DNA and RNA, ribonucleic acid and deoxyribonucleic acid. The difference between ribonucleic acid and deoxyribonucleic acid is the oxygen over here. Because, as you know, ribose sugar contains so many oxygen atoms. One of the oxygen atoms is now substituted with the nucleobase already. The other OH is then condensed with the phosphoric acid. The last OH over here as well condensed with the phosphoric acid. You have one OH left in the structure. For RNA or ribonucleic acid, this is actually the structure of ribonucleic acid. But what is the DNA? The structure of the DNA is the deoxyribonucleic acid. You just lack of this oxygen. So by evolution, right, the very primitive living organisms like some of the viruses, you have only RNA in their cells. But with the evolution for bacteria upward to human like us, the genetic is controlled by DNA instead. So the evolution just decided to cut the oxygen, this oxygen out. So in the instead of OH, you have just H, and actually you just erase it out, right? Because in a line structure like this, if you draw nothing here, that means you have H2, right? You have two hydrogen attached with this carbon. So this is the structure of DNA. So this is differences between DNA and RNA. Just only the oxygen was cut out at this position. Okay, no? Now this is the polynucleotide. Both polynucleotides type DNA and RNA, we have a very unique character of physical interaction or of the intermolecular interactions, which is the hydrogen bonding. So now next we're going to look at the hydrogen bonding system in our DNA and RNA system. Now, as I mentioned earlier, that our nucleobases adopt sp2 hybrid for all atoms in the ring and also around the ring as well. And this is how the molecules fix the position of everything. I mean, if you look at adenine here, instead of drawing adenine like this, I just expand the NH2. And as I say that the NH2 is sp2. So both hydrogen atom around nitrogen is extended onto 120 degree by trigonoplanar shape. And also, if you look at nitrogen over here, sp2, that means electron pair is in sp2 hybrid and pointing outward to the right hand side. This electron pair pointing outward here, down here, 120 degree. Again, this is another example. This is the guanine. As you can see, guanine, you have oxygen atom over here, and because of sp2 hybrid, electron pair of oxygen atom pointing 120 degree toward the right hand side and upward to the left slightly. NH over here is sp2 as well. So electron pair is in p orbital for the resonance, and H here pointing 120 degree to the right hand. Last group, amino group here, electron pair is in p orbital in order to conjugate with the cyclic structure pi conjugator system. So two of the hydrogen atom pointing 120 degree away from the ring. So as you can see, hydrogen in each system over here is connected with nitrogen atom, and hence your hydrogen atom is slightly positive, right? Because En of nitrogen atom is higher than hydrogen atom, and nitrogen atom can then withdraw electron out of your hydrogen atom, make your hydrogen atom positive, 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 and positive. So if your hydrogen atom is positive, then it can making hydrogen bond with other atoms with very high electron density. High electron density is like this: electron pair of nitrogen atom, electron pair of your oxygen atom. So this hydrogen atom is called hydrogen bond acceptor. So this hydrogen atom, which is slightly positive, is hydrogen bond donor, and this electron pair with negative charge is a hydrogen bond acceptor. So as you can see, the direction of hydrogen bond is this way, is this way. This is donor, this is acceptor. This is hydrogen bond acceptor. This is hydrogen bond donor, and this is hydrogen bond donor. Okay. Hydrogen bond is not, the character of hydrogen bond is not only the 180 degree over here, it's about the size of hydrogen bonding as well. Normal NH bond and OH bond is about 1 angstrom, but a hydrogen bond between H and O and H and N is about 2 angstrom. I can say that the hydrogen bond is about half the strength of conventional covalent bonding. So now, as you can see, we have hydrogen bond donor here, acceptor here. So if you have something with hydrogen bond acceptor up here and with hydrogen bond donor down here, it can then automatically locked up with this molecule. And again, this is acceptor, donor, and donor. So if you have hydrogen bond donor, acceptor, and acceptor over here, you can then locked with this molecule. So we have some alternatives down here. As I show you, I use purine base as the first strand. The DNA and RNA can then conjugate with the complementary bases on the right hand. Okay, so if you look at here, you have hydrogen bond. I would say NH2 is hydrogen bond donor. Electron pair is hydrogen bond acceptor. Right. For this molecule, you have electron pair as hydrogen bond acceptor. H over here as donor. H over here as donor. So as I extend the chemical structure like that. Okay. For this uracil, this is electron pair act as hydrogen bond acceptor. H over here is donor, and electron pair over here is the hydrogen bond acceptor. So you have acceptor, donor, and acceptor. And again, for thymine, acceptor, donor, and acceptor. For this cytosine, you have donor, electron pair as acceptor, electron pair as acceptor. So donor, acceptor, acceptor. So to be clear, as you can see from the guanine and cytosine, acceptor and donor matched. Donor, acceptor matched. And again, donor and acceptor, again, matching together. So that means your guanine over here can make hydrogen bonding 3 position with this cytosine, right, perfectly. So I would move the cytosine to over here. At the donor position, NH2, I can draw it like this, HN. Because hydrogen bonding is 180 degree, right? So H is over here, and then down here to the ring. And then you have cyclic ring, the pyrimidine ring down here. So the pyrimidine ring is like this, okay? So this is your pyrimidine ring, and the pyrimidine ring here will attach to the ribose sugar, which I will not draw the things completely. I just say ribose over here, you know. So after that, we have cytosine. So the amino group connecting with the double bond N, double bond here, and this is double bond O. So you have electron pair of nitrogen and oxygen over here, and constructing hydrogen bond, 3 hydrogen bonding. So as you can see, because of 120 degree of the sp2 hybrid, you now constructing hexagonal structure. Two of the hexagon, but your hexagon is quite elongated on one dimension because the hydrogen bond is quite longer than the normal covalent bonding, right? So instead of the same angstrom over here, this is twice the length, right? So you have this kind of thing. So the distance between N and O over here is about 3 angstrom because, as I said, conventional covalent bond is 1 angstrom and the hydrogen bond is about 2 angstrom. So that means the dimension, the length between N and O, the distance between N and O is about 3 angstrom roughly. Okay, so as you can see now, your guanine is matched with the cytosine with 3 of the hydrogen bonding. Okay, so now if you have time, you should draw the hydrogen bond system between your adenine and one of this cytosine, uracil and thymine is about the same, right? Because thymine is actually the methylated version of the uracil. Starting from uracil, you're doing methylation. That means you put the methyl group on here, this position. You have thymine as a product. So thymine is the methylated uracil actually. So you should pick one of this, uracil or thymine, and draw the hydrogen bond system here on the right hand. Okay, I give you 5 minutes maybe. Okay, so if you finish, I will continue. If you not, you just pause the video. Okay, now I'm going to give you the answer. So as you can see, we have donor and acceptor, right, on top and bottom. Unlike your guanine, you have 3 positions: acceptor, donor, and donor. But this is donor, acceptor, and nu, nothing here. So what you have to use is acceptor and donor. As you can see, we have acceptor and donor. Acceptor on top, donor in the middle. At the bottom, you also have acceptor, but you have nothing over here, but that's fine. So that means you can have maximum 2 hydrogen bonding in the system. Now I will draw the thymine. Okay. For thymine, first of all, on top you have donor over here that is matched perfectly with the electron pair of oxygen at the acceptor. Okay. And the acceptor oxygen is now connecting with this one. So the N here will go to the ribose with the glycosidic bonding. Okay. Now we are drawing the thymine. Okay. So you have double bond over here, methyl group over here, and with the ribose. And then you have double bond O over here. And for this, you have an H. Right? An H over here. So as you can see now, thymine and adenine, you can lock them up together with 2 hydrogen bonding. Okay. Now as a result, as you can see from the structure, actually ribose sugar and ribose sugar over here link together past the phosphodiester bond around here, right? And you have 2 chain of the nucleotide matched together, having a kind of hydrogen bond network together. Okay, so what I want to summarize here is that donor and acceptor hydrogen bonding matched perfectly between nucleobases, okay, and you can constructing this kind of structure. And because the length of hydrogen bond is fixed, right? So the distance between N and N here is fixed. The distance between purine and pyrimidine is fixed. The distance between ribose and ribose is fixed. So everything is fixed. So that means this chain and this chain is parallelly attached themselves together in a fixed structure with the same length for the whole series. Okay, no? And what else? So that's all about the basic structure of the nucleotide, nucleoside, nucleobases, and also for the nucleic acids. Now, from this, I have so many questions for you to think about it as a homework. Okay? Now let's see the question that I will give you as a homework. In this topic, I have two questions for you. First of all, very simple one. The question is, why can't the RNA construct a stable structure like double-stranded helix like in DNA? Because as you know, the DNA can, when you see the structure of DNA, we normally draw it like double-stranded helix, very stable structure like that. But we never draw structure of RNA in that kind of form. Even though RNA can also making hydrogen bonding like this. As you know, when you have DNA transcription, right? Starting from DNA, you synthesize the RNA. We call it as RNA transcription. No? So RNA from the nucleotide of RNA is attached hydrogen bonding together with the DNA and then polymerize them together, making the RNA. That means RNA can have hydrogen bonding system with the DNA. Or RNA and RNA as well, like transfer RNA and the messenger RNA. When you want to do the translation to change the coding of messenger RNA to synthesize the proteins, right? So transfer RNA have to making tricodon structure with hydrogen bonding with the messenger RNA. That means your tRNA and mRNA can have hydrogen bonding in this kind of thing as well. But you never drawing like stable helical structure of two-stranded RNAs. Never, right? But what is the reason behind it? Right? Think about it. That's the first question. The second question is, I show you here is a structure of inosine. Inosine is commonly found in transfer RNA or tRNA. And yes, because of the structure is very similar to the ACGTU base, right? So that means this one can also forming this kind of hydrogen bonding system with some bases here. Okay? The question is, if I want to make base pairing structure between inosine here and the cytosine, okay? So it's quite the same as here in the picture showing here, right? So what I want you to do is drawing the structure of the base pairing between I and C. C is here. I have ACGTU over here. T and U is very similar, right? Because this is T. If you cut down the methyl group here, you have U. Now what I want you to draw is the hydrogen bonding system between C and I or inosine. Okay, that's your assignment. Okay, then I will come back and show you the answer in the next video.